Well, hello, welcome again to Math 315. This is the fourth recording in this section 9 on the real numbers. And we finished off last time giving some proofs that various numbers were irrational, such as log of 7 to the base 2, etc. And I wanted to do a fairly difficult example, but it's a fairly classical and very important little piece of mathematics. You won't need to be able to reproduce it. If you can follow through some of the argument, the logic, then that will be a nice thing. We're going to give a proof here that the number e is irrational. There are a number of proofs of this. This is I think one of the earliest ones. Goes back a couple of hundred years, but it's an interesting proof and not too difficult to try and follow. So I'm going to go back and recall the Maclaurin series that we did earlier, and we saw in that section that we could find the Maclaurin series for e to the x, and had this beautiful series which is so lovely and very simple that e to the x has a Maclaurin series of 1 plus x on 1 factorial plus x squared on 2 factorial plus x cubed on 3 factorial plus forever, and this converges for all real x. So you can put any value of x you like into the right hand side, it converges back to e to the x. And as I've mentioned, this is how your calculator calculates e. So when you ask your calculator for e squared, it has a built-in program that simply puts 2 in place of x in the series, takes the first 10 terms and gives you a good approximation to the answer. For us, I'm going to put x equals 1 in, and that will give us a lovely infinite series for e, which now then, putting x as 1, we get e as 1 plus 1 on 1 factorial, 1 on 2 factorial, plus 1 on 3 factorial, plus forever. So this series converges back to the number e. Now we're going to prove that e is irrational, and as we've done in all the earlier proofs, we do this by contradiction. So I'm going to suppose that e is a rational number, and that's going to hopefully lead us, with a bit of hard work, to a contradiction. Now if e is rational, then I can write e as p over q, where p and q are positive whole numbers, they're integers. Now I'm going to now choose an integer, capital N, a whole number, that's bigger than the denominator of our supposed fraction here. So if q turned out to be 105, then I take n to be 106. You just take some number that's bigger than the q. Now I'm going to use our series here, and I claim that this is p over q, so I'm going to take this number minus part of this. I'm going to terminate this at 1 over capital N factorial. This capital N is the number we chose up here. So I'm going to take this supposed version of e as a rational number minus just that many terms of the series for e. Well, what do I have left? Well, I've got left all the other terms. I've got 1 on the next one factorial, plus 1 on n plus 2 factorial, plus 1 on n plus 3 factorial, plus and so on forever. Okay, so just think about that. I'm just taking off the infinite series here. I'm just chopping it off here after the nth term here and subtracting it off, and I'm left with all the other terms. Now the key to this now is I'm going to multiply both sides by n factorial. Now when I multiply p over q, remember what n factorial means. It's all the numbers from 1 up to n. And one of those numbers has got to be q because I chose n to be bigger than q. So when I multiply the n factorial times p over q, then that q, that factor q, is somewhere in the n factorial. It'll cancel out, and I'll be left with a whole number. I'll be left with an integer. So when I multiply, and by the way also each term in the bracket here, every term in the bracket here will also cancel. The denominators will cancel with the n factorial, and so that times n factorial is a whole number, that times n factorial is a whole number, that times n factorial is a whole number, and so on, and that times that of course is just 1. So that means when I multiply all this by n factorial, So I'm doing down here. This is going to be a whole number. It's going to be an integer. Now I've multiplied the left-hand side by n factorial, so I multiply the right-hand side also by n factorial, and I get that expression. Now what I'm going to do now is I'm going to try and see how big is this mess here. What can I do with this thing? Well, firstly I can simplify it. N plus 1 factorial on the bottom is n plus 1 times n factorial, so you can cancel them out and get n plus 1. You can write this as n plus 2 times n plus 1 times n factorial. Cancel it out, you just get n plus 2, n plus 1, and same with all the other terms, plus dot dot dot. Now what I'm going to do now is I'm going to do what we often do with inequalities. I'm going to use the inequality sign to throw away a little bit of the rubbish. So I'm going to replace that. I want to see an n plus 1 here. So 1 over n plus 2 is less than 1 over n plus 1. So I'm just replacing the 2 here with a 1. And now I do the same here. I'm going to replace the 2 and the 3 both with 1s. And then I do the same all the way through. Because the point being then, I now get 1 on n plus 1 plus 1 on n plus 1 squared plus 1 on n plus 1 cubed, and so on. And this, of course, is a geometric series, and we know how to sum geometric series. So let me finish this off then here. So that's what I've ended up doing. So I've just recopied this here. I've recopied the same thing we had in the previous line there, so we can look at it again. So this thing here now is a geometric series. It's got, there's the first term, so the sum is a over 1 minus the common ratio, which is n plus 1. So it's a geometric series with that sum. And if I simplify this by multiplying top and bottom by n plus 1, then I leave you to check, it all collapses down to 1 over n. So let's just carefully put that together then. It says then, looking back to where we were, it says you get this expression here, which is a whole number. This is now less than 1 on n. Now the point, of course, is that if n is bigger than 1 on n, this number is going to be a positive number, but it's less than 1, strictly less than 1, and so it can't be an integer. So if n is 2, for example, this is just a half. And that says the left-hand side, which was an integer, is positive, don't move the e there, is positive and less than 1. Well, you can't have an integer which is positive and strictly less than 1. There's no such thing. And so this is a contradiction. It shows that e could not be rational. Now that's a difficult proof, but it's one worth thinking about and going over and see if you can follow the steps of it. The basic aim of it was to show that this quantity that we had back here, this quantity here that we had in this expression, was a whole number that was positive and less than 1, and there is no such whole number which is positive and at the same time smaller than 1. Okay, well, this brings us to our next little section, which is on continued fractions, and this is yet another way of representing real numbers, is to use things called continued fractions. These are great fun, in fact, continued fractions. You can do lots of interesting things with these. We'll just do a little bit, but there's lots and lots written about continued fractions. This turns out to be a much more accurate than the decimal representation. And in fact, it is exact for rational numbers, for all rational numbers. So I'm going to demonstrate this representation by looking at various examples. So I'm going to have, here's an example of a continued fraction. You have 3 plus 1 over 1 plus 1 over 5 plus 1 over 7. So you get these nested fractions. It's sort of like a tower of fractions here. Now that gets very cumbersome to write, even to do it in this print here, it's very hard to read and difficult to write. So what we do is we write this as 3, that's the whole part. We put a semicolon to split off the whole part, and then we just write down the partial, what are called partial quotients, the 1, the 5 and the 7. So 1, 5, 7. So when I see this, I mean 3 plus 1 over 1 plus 1 over 5 plus 1 over 7. Now if you simplify this, so that is you put you add these two fractions, 5 plus a 7th, which is 36 on 7, and you turn it upside down, so you put 7 on 36, and then you add that to 1, that gives you 1 over 43 on 36, and when you turn that upside down you get 1 and 36 on 43. So this is a way of writing this fraction. Now these numbers 1, 5 and 7 are referred to as the partial quotients. Now to reverse the process, well, we simply do the following. I'm going to take away the 3, forget about, we'll put the 3 in later, just work with the fraction. So you take the reciprocal of 36 on 43, which is 43 on 36. You do the division, it goes 1 remainder 7, so it's 1 and 7 on 36, so you hang on to the 1. Now you take the fraction part here and continue on by taking its reciprocal, which is 36 on 7. Now that goes 5 times remainder 1. Keep the 5. Now take the reciprocal of 1 over 7, well that's just 7 over 1, which is 7. And there are the numbers we wanted. So 3 and 36 on 43 is just 3, and then it's 1 over 1 plus 1 over 5 plus 1 over 7, which we're writing in this form up here. So the underlined numbers here are called the partial quotients. Now as mentioned, this representation turns out to be finite for rational numbers. That is, it terminates, it stops for all rational numbers. Now you know that there are some rational numbers in decimal form that you have to that are repeating and just continue on forever. But for the continued fractions, for every rational number has a finite continued fraction that doesn't continue on. Since the size of the denominators at each stage is getting smaller, every time we did the division and turned it upside down, the fractions got smaller. And that means eventually they're going to go to 1. So for real numbers, well, we do the following, and I'm going to take you through. I'll show you how to do this also on the calculator in a moment, but just doing it bare hands, this is the way we're going to take root 2 and find out what its continued fraction is. Okay, so what we do is this. We say root 2 is about 1 point something. It's 1.4142. So it's 1 plus something. So we copy down the 1, and then I want it to be equal, so I've got to patch it up. I'll have to add a root 2, so I get a root 2 in both sides, and I'll have to subtract 1 to kill off that 1. So we'll hang on to the 1, and now we look at root 2 minus 1. We take 1 over this number, so we get 1 over root 2 minus 1. And now I'm going to rationalise the denominator. So I'm going to multiply this by root 2 plus 1 on root 2 plus 1 to rationalise the denominator. So I get root 2 plus 1 on the top, and the bottom I just get 2 minus 1, which is 1. So in other words, this is just 1 plus root 2. Now, how big is 1 plus root 2? Well, 1 plus root 2, well, that's about 2.4, so it's 2 and a bit. So copy down the 2, and then this is supposed to equal this, so I'll need to add in a root 2, and then I've got 2 and I've got 1, so I'll have to subtract a 1. Well, now you keep this number, and now I'm going to take 1 over this number. But of course that just gets me back to here again. And so I do all the same calculation and I get another 2. And then I repeat, I take 1 over that and I repeat the process. And so as a continued fraction, this is going to be 1, that was the integer part back up here, semicolon, and then I'm going to get 2, and then I'll get another 2, and another 2, and so on forever. We're going to write that just with a bar notation of 1 semicolon 2 with a bar. That simply means the 2 goes on forever. So that's the continued fraction expansion, as it's called, for root 2. Continued fraction expansion for root 2. So just to do a couple of more examples, we're going to find the continued fraction for 103 on 37. Now this is a rational number, so we'd expect this to have a finite continued fraction. And this was probably not a great example to do because it takes a bit of arithmetic, it takes a while, but anyway it certainly shows the method. So 103 on 37. So I do the division, this goes twice 37, so that's 74, and I get a remainder of 29 on 37. So hang on to that number and then look at the fraction. We take the fraction, we flip it upside down, take its reciprocal. Again we do the division, it goes once, and then the remainder is 8 on 29. So hang on to that number. Take this one, flip it upside down, we get 29 over 8. Notice that the denominators are getting smaller every time. So we divide this by 8, 8 threes are 24, remainder of 5. Keep the 3, take the 5 eighths, flip it upside down to 8 fifths, that goes 1, remainder 3. Keep the 1, turn it upside down, that goes 1, remainder 2. Keep the 1, turn this upside down, I get 1 plus a half, and finally, when I turn this upside down, I get 2. So that's going to give me, then I put it over the side here, so there's the continued fraction for 103 on 37. You just copy down the digits. The integer part was 2, and then you semicolon, we had 1, 3, 1, 1, 1, 2, and it stopped there. So there is the continued fraction expansion, as it's called, for the rational number 103 on 37. And notice, of course, it stops, it terminates, because the denominators keep getting smaller, and eventually they're going to hit 1. The second example here was 2 plus root 3 to get that as a continued fraction. Now, by the way, you can get the continued fractions of these on your calculator. I'm going to do it, in fact, that's the way I'm going to do this one, by using the calculator. So here's the number, 2 plus root 3. So have your calculator handy. Whack this in your calculator, get as a decimal. You should see 3.732 ... Keep the 3, copy down the 3. Now on your calculator, take this number and subtract 3. So you take this minus 3 and then push the 1 over button on your calculator. You should see 1.366 ... Keep the 1, copy down the 1, subtract 1 from this on your calculator, push the 1 over button. You should see 2.732 ... Copy down the 2. On your calculator, take this number, subtract 2, push the 1 over button, you'll get 1.3666. And look, hang on, that's the same as what we got up here. And so the pattern is going to just circle around. So it's going to go 1, 2, 1, and then 1, 2, 1, and then 1, 2, 1 forever. Sorry, it's going to go 1, 2, 1. So it's going to go 1, 2, 1, and then we get back to here. So 2, 1, 2, 1, I should say, forever. So the continued fraction then has got 3 is the integer part. The next thing you got it was a 1, and then a 2. And when you did the next operation, it got you back to here again. So that's going to be, that's your 1, and that's 2, and it's just going to go 1, 2, 1, 2, 1, 2 forever. And we're going to write that as 3 semicolon 1, 2 with a bar over it to show that that repeats forever. Now, the continued fraction for pi is amazing. Again, you can do this on your calculator. You put in pi, you get 3 point something, subtract 3, push the 1 over button, you get 7 point something, subtract the 7, push the 1 over button, you get 15, and then you'll get 1, and then to your horror, you get 292 suddenly pops out. Where does that come from? What pattern is there? There isn't one. And so on. Now, the interesting thing is you can now get some interesting approximations to pi from that, because if you just forget about this much and just take 3 and 1/7, you get 22 on 7, which is that approximation. It doesn't equal pi, but that approximation to pi that you often use in junior maths. You approximate pi by 22 on 7. If we take the next term, then I get 3 plus 1 over 7 plus 1 over 15. Add these together, you get 106 on 15. Turn it upside down, you get 15 on 106. So there's another decimal approximation to pi. Now, by the way, this is a decimal, it's 3.1415, and then it goes 09, so on. Pi is 3.141592, so it agrees with pi to 4 decimal places. Well, if you want to do another one, I'll leave you to do 3 plus 1 over 7 plus 1 over 15 plus 1 over 1. And you'll get another approximation to pi, which I think is the one that Archimedes got. Not by using this method, of course. The other example, so that was part C here. And the other interesting thing to look at here is the golden ratio, which is 1 plus root 5 on 2, and this has a remarkable continued fraction. You may have come across this number. If not, you should Google golden ratio and learn about it. It's a lovely, fascinating number, which it turns up in high school maths. Well, what do? I just do it on the calculator. You plug this in, you get 1.618. You subtract 1, push the 1 over button, you get exactly the same thing. And this just keeps repeating. In other words, the continued fraction for this amazing number, the golden ratio, turns out to be 1 with a semicolon and then followed by 1s. In some sense, it's the simplest infinite continued fraction, and it happens to converge back to the golden ratio. Okay. So I put a number of ones for you to have a look at there. So here's some further examples here. The square root of 3 turns out to be 1 semicolon 1 2 1 2 1 2. We've had a look at that one before. Root 5 turns out to be 2 4 repeater, so it's that one. Root 7 is more complicated. It's 2, and then you get 1 1 1 4 1 1 1 4. There is a pattern which is very surprising. No pattern for pi, but for E, the pattern is you start off with 2, then you get 1 2 1 1 4 1 1 6 1 1 8, and the pattern continues 1 1 10. Well, this is quite mysterious, because after all, why should E have a nice continued fraction with a nice pattern in it, but pi doesn't? Pi has a horribly complicated continued fraction with no pattern. Cube root of 2, to see what happens with cube roots, well, these don't repeat. These are all over the place. You get 1, and then 3, 1, 5, 1, 1, 4, 1, 5, 8, 1, 14. It's all over the place. When you get to these square roots, the quadratic irrationals, these have very nice continued fractions, but the other ones don't. Now, as I mentioned before, it turns out that rational numbers then have finite continued fraction. So we have a little theorem here that if x is rational, then the continued fraction for x is terminating. And indeed, so it looks like this. It just got an integer part and then it's got something but it stops. Irrational numbers have continued fractions that do not terminate. That means we could define the set of real numbers to be the set of all possible continued fractions. Those that terminate give you the rationals, those that don't terminate give you the irrationals. The main problem with this is how to define addition and multiplication of real numbers using continued fractions. That's very difficult. The real numbers have basically two types of continued fractions. Real numbers of the form a plus b root c, where just it only involves a square root, where a, b and c are rational and c is not a square. These have recurring continued fractions. As we've seen, the continued fraction for the square root of n has a very special form. It repeats, but it actually goes up and then the numbers go along and then they reverse back to where you start from, and the last one is double the constant term. For example, the square root of 54 looks like this. It's 7 semicolon 21612, so it goes up and then back down again, and you double that number and that goes on the end here. It's very cute. Root 53, similarly, you've got 7, then you've got 3, 1, 1, 3, so it's symmetric, and the 7 doubles give you the 14. Well, I've done some examples of these on the other page there. Finally, we can convert recurring or eventually recurring continued fractions back to quadratic irrationals in the following way. So suppose I give you one of these continued fractions that's repeating. Can we get back to what rational number it came from? And I'll do an example of that. We'll do some more of those in the tutorial. So x is 0 semicolon 5 bar. So that simply means that's 0 plus 1 over 5 plus 1 over 5 plus 1 over 5. And that simply means this is 1 over 5 plus this bit here, but that bit here is exactly what I started with. 1 over 5 plus 1 over 5 plus 1 over 5, so that's x. So that means I can write x as 1 over 5 plus what I started with. Got to think about that a little bit. Now you can cross multiply here, you get 5x plus x squared is 1, rearrange to get a quadratic, and then you can use the quadratic formula if you like. You get minus 5 plus or minus root b squared minus 4ac is 29 on 2a. Now the continued fraction is positive. This is clearly going to be a positive number, so we don't want the negative here. So we take x as root 29 minus 5 over 2 because x is positive. And you can check by using that method I mentioned before, using your calculator. If you shove this in your calculator and use the algorithm, you'll see you get 5 as the continued fraction. And we'll do some more of those in the tutorial.